Okay, good morning. We're going to get started with a couple of problems that'll be reviewed for the exam tomorrow, and then we'll move into some new material. So we'll do one projectile motion and one velocity addition problem, then move into some new material. The new material will not be on the exam Friday, but we'll get started on it anyway. Okay, so we've got this this problem here. A cannon is going to shoot some kind of projectile at a speed of 1,000 meters per second at a mountain that's in front of it. So the picture is going to look something like this. And the mountain is over here. And the cannon is firing here. This is 1,000 meters per second. And the projectile lands up on this hill somewhere. So this is 2,000. And this was 800, I believe. Yeah. And they want to know what angle. So go ahead and set it up. See what you get. See how you would set this up. Let's take a few minutes. Think about this problem. Remember, we're launching this projectile. They tell us the initial speed, but not the angle. And we know the distance, x and y distance to where it lands. We're trying to find theta. So I assume most of you would attempt this using the equations that we've learned. So what's the first thing you have to do? Define your origin and your positive directions. I would probably pick this. Maybe you did too. There's my origin. There's my positive x direction. There's my positive y direction. Now, once you've done that, you can fill in your tables, right? go ahead and fill in those tables. What's the X and Y coordinate where the particle starts, where our projectile starts? It's at the origin, right? The X and Y coordinate where it ends up, 2000 in the X and 800 in the Y. V sub X and V sub Y. I think it's best if we write that in terms of theta. It seems, at first, it seems like you have two unknowns here. You don't know V initial in the X, you don't know V initial in the Y, but really there's only one unknown, and that's theta. So we'll write this as 1000 cos theta and 1000 sine theta. V final, we don't really care about. Acceleration in the X is 0. Time, we don't know. Acceleration in the Y is just gravity. This object is in free fall. Gravity is the only thing acting on it. So it's in the negative direction, and time we don't know. So normally what would we do? We would use one of these directions to get the time, plug it into the other one, and solve for whatever we're looking for. But in this case, we have two unknowns. We're missing theta and we're missing t, but we're going to end up with two equations. So we need two equations that have theta and t in them, and then we can solve simultaneous equations. So a question about the pictures being provided. I try to provide a drawing like this in the exam if I think it's helpful. I would have provided a drawing for this problem. Okay, so in my X direction, I pick an equation that's missing V final, and I get this one. There's no acceleration in the X direction. And so if I plug in my values here, what do I get? 2000 is 0 plus 1000 cosine theta times t. So t is 2 over cosine theta. Then in my y direction, I use the same equation, right? I'm looking for an equation that's missing v final. So I've got y final is y initial plus v initial t, that's in the y direction, plus 1/2 a t squared. And so what do I get? I've got 800 is 0 plus 1000 sine theta t minus 4.9 t squared. And if I plug my t in over there, I get this crazy equation, 1000 And normally what I would say is the physics is done at this point. Now it's just math, solve for theta. But if you look at that equation, that is nasty. I don't know how you're going to solve that. I guess maybe graphically on a calculator you could graph it out and solve for theta that way. I'm not sure. But you can see when they ask for the angle in one of these problems, it becomes very tricky. You end up with simultaneous equations, and it's kind of like, remember when we talked about one-dimensional kinematics problems, and we said you had a race where one object was catching another one and passing it, something like that. It became kind of messy with equations. But if you took the graphical approach and solved it that way, it becomes much easier. Well, let's take a look with this problem with the graphical approach. The graphical approach, I agree with two-dimensional kinematics problems, is a little trickier. But for this problem, I think you'll see that it gives you a cleaner solution. So so our equation is okay. So this is the equation that we used up above, right? But we didn't write it in vector form. We just wrote it as components. X final equals X initial plus V initial in the X direction times time plus 1/2 acceleration in the X direction times T squared. And we did the same thing in the Y direction. We split this equation into components. But if we do it in vector form, and it's always good to start out at the origin, which we did, that we happened to pick the origin as our starting point. So that means that the initial position is 0. So our final position, which we know what the final position is, right? It's 2000 in this direction. This is 2000. And it's 800 in this direction. I don't know, how about there? 800 in this. So our final, I know what our final is. Our final is this vector right here. It's the vector that points to my final position. And I know I have to add two vectors to get to that. V initial times time, and V initial times time, and 1/2 AT squared. And where does the direction come from? It comes from V initial and from A. And I know my A points straight down. So this one is going to give me a vector over here that points something like this. So that's going to be my 1/2 AT squared. I'm not, drawing anything to scale here. I'm not sure exactly what it's going to look like. But and this one is this vector. And that means that this angle is theta, right? Not the one down below there. Here, let me write it like that. So if you do this, this is the equation you get. This is a right triangle. So this side squared plus this side squared has to equal this side squared, right? It's a right triangle. So I've got 2000 squared plus, what is 1/2 AT squared? It's 4.9 T squared plus 800 has to equal V initial is 1,000, right? That side squared. Okay. So if you do this and you work it out, you get a very simple quadratic equation. I got this as my equation. I got 24.1 t squared minus 992 160 t squared. Oops. This is t to the fourth. T squared plus 4,640,000 equals 0. So I got t is plus or minus 2.16 or plus or minus 202.9. That's just a quadratic, right? So that was relatively easy to solve. And I got my times. I can throw away the negatives, right? Negatives don't mean anything. Why do I get 2? Why do I get 2 times? Because it's going to get, where's my picture? It's at 2 seconds, where are my times? 2 seconds and 202 seconds. At 2 seconds, my projectile is right here at y equals 800 meters. Then it keeps going, and at 202 seconds, it's right here. It's at y equals 800 meters again, but coming down this time. So that's why we have 2 times. So you have to think about it. Sometimes you get 2 times and it's obvious. One is negative, one is positive, and negative time is not physical, right? It's meaningless for our problems here. We're looking for a real solution. So you throw out the negative root. Sometimes you do a problem and you get 2 positive roots and you have to think about it a little bit. Well, wait a minute, which one makes sense here? Oh, I've got 2 times because I'm going to hit on the way up, I'm going to hit that y value, and then on the way back down, I'm going to hit that y value. And you have to reason through and think about which one you need. Questions? Let's see. Why is gravity not negative? It's negative. It's right here. It's pointing down, right? I have it as the I took the direction into account with that. This is the magnitude. 1/2 at squared is the magnitude of that vector, right? We okay with that? You're not. You don't want to. All I'm doing is with this is taking a right triangle and saying a squared. That's this, right? Plus b squared, right? Equals c squared, right? That's all I'm doing here. So these are just lengths of a triangle. Don't put a negative number in for a length of a triangle, right? It's think about how you're solving the problem. The direction is taken into account with the arrow, the direction of the arrow, and these are magnitudes. Yeah, you're allowed calculator for the exam for sure. Okay, so now you take that time, we've got 4 times here. We've eliminated the 2 negatives, those are not physical. And we've said that we have 2 positive roots, 2 seconds and 202 seconds. 2 seconds is not the one we want, that's the one that hits on the way up. We want the one on the way down. And so we use t equals 202.9. And then we plug that into our x motion. And we get 2,000 is 1,000 cosine theta times time. And so theta is actually, I jumped the gun here a little bit. I jumped the gun. You want to, in this problem, actually, I think there are two solutions. So if t is 2.16 seconds, you get a low angle. Should have checked my notes first. And if t is 202.9 seconds, you get a high angle. So there are two solutions. You would use either, you have to check either one, because you can get, remember with projectile motion, you can get, there's probably a graph in the book that shows to get a certain range, if you launch a projectile and it ends up here, you could also launch it this way with the same speed and it gets to the same place. Okay, there are two different angles you can pick that will have it land in the same place with the same initial speed. And those, if you're starting and ending at the same height, those two angles would add to 90 degrees. So if one was 30, one would be 60, that kind of thing. But in this case, we're not starting and ending at the same height, so it's a little different. But we would have two different angles. We could have a very low trajectory that got there, or we could shoot it way up and get it there in the same thing. Okay. Anyway, the point was, pick whatever method you prefer. If you got to this point and stopped, that's okay with me. The physics is finished at that point. The point is that if you like the graphical approach, there are a few cases where it's really nice. And it helps you find an answer that's much more difficult to find otherwise. So that's the point here. But you know, if you like the equations, stick with the equations. That's fine. It's just a nice technique. If you do it with the equations, I don't know, I think you'd be stuck right here. Question is, where would you stop? Unless you can figure out a way to solve that, you know, graphically on your calculator or something, I think you'd be stuck right there. I would be. Okay, so the graphical approach helps you find that answer. All right, let's take a look at you do not need the graphical approach for the exam. Pick whatever you like. Would they have the same velocity at t equals 0? Yes. Yes, same velocity at t equals 0. So this is the question about this. We're taking the side, we're using our normal equation here, right? So we have a 1/2 a t squared. Well, a is 9.8, so 1/2 a is 4.9, right? So we have a 4.9 t squared. And so when I draw it graphically, the length of this side is 4.9 t squared, right? That's what this is. 1/2 a t squared, right? The length of that side. And so I want the length of this whole thing. I want the length of this whole thing. So I add that. To 800, because that's the length of the lower one, to get the length of this side of my triangle. And then I just use Pythagorean theorem. It's a right triangle. This is a right triangle. So I square one side, square the other side, add them together, and that's the square of the hypotenuse. And then the hypotenuse is 1000 t squared, because the hypotenuse is just v initial times time, right? V initial in the x direction is 1000 sine theta. V initial in the y direction is 1000 cosine theta. But here I don't care about x and y. I just want v initial. So it's v initial is 1000. It was given. Okay. All right. Anyway, if you like the graphical approach, try it out. If you don't worry about it. But it does, there are certain few weird key problems where they're really nice. The graphical approach is nice. All right, should we do a vector addition? Or should we do our application? Let's do our application of the day here. Projectile motion. So projectiles, right? That's the main application. We know that anytime something's flying through the air, we'd have to be able to figure out where it's going to land, things like that. And we're learning to do that. Of course, real life situations are a little more complicated with air resistance and things like that, but eventually we will learn to deal with that. Roller coasters. So the shape a roller coaster takes is calculated very precisely based on the speed and things. So you know, right, if you take take some object and slide it off the table, it's going to follow a parabolic path and hit the ground over here, right? So if you built a track right underneath that object that followed that exact parabolic path, the object would just fall right along the path and feel like it's in free fall. So that's what they do with roller coasters. A roller coaster your car, the roller coaster car, has a certain velocity at the top, right? They know what velocity that is. They design these roller coasters very carefully, right? They know the velocity it's going to have at the top. Well, if there was no track there and it was given that horizontal velocity at the top, they know that it would follow a certain parabolic path. So they build the track with that exact parabolic path so that when you go over the top of that roller coaster, the peak, and start coming down the other side, it feels like you're in free fall, because that's the exact path the car would be taking if the track wasn't there. So you get that weightless feeling. Same thing happens if you go over a bump in the road sometimes, or you kind of get that weightless feeling if it's just right for that instant. But these roller coasters are designed with that path in mind. So anyway, we're learning about things like that. Now, this next one, I put all this text in here. If you're interested in this, check it out, read it later. But this is kinematics on steroids. This is such a cool application. You've got to check this out. So baseball started using something called Statcast, and we're going to check out this video. But what they do, they put cameras all around the baseball stadium, filming the field. And these cameras are taking pictures, and computers are analyzing where things are, where the ball is, where the players are, everything. And in a very short period of time, the computers can calculate how fast is a runner accelerating? How fast are they moving when they're stealing? What's their maximum speed when they try to steal second base? How fast was the ball coming off the baseball bat? What the angle is? It'll predict if it's going to be a home run or not before the ball actually makes it out over the park or is out of the fence or not. It predicts. Anyway, really, it would even tell you how fast the umpires were moving if you wanted to know that, but nobody wants to know that, right? So let's take a look at this video I've got. So this is baseball. If you're not familiar with baseball, let me set the stage for you because this is a very exciting game. It is 2-1. The visiting team is winning. They are up by 1 run. It's the bottom of the 9th inning. You can see over here in the score in the upper left. That means this is it. This is the last chance for the home team to try to tie or win the game. There are 2 outs. 2 outs, bottom of the 9th inning. The tying run is at second base. The winning run is at first base. If this batter makes an out, the game's over. Atlanta wins. If this batter gets a hit, the game is probably tied. And if the hit is a long one, it goes through to the wall or something, they win the game. Home team, the Mets, will win. So let's see what happens. Are you excited? Let's see.
Fly ball,
that's a good one.
Center, Hayward coming, dives, and catch it, yes! What a grab by Hayward to end the game! Holy smokes.
So let's analyze this. Okay, he hits the ball within seconds, okay? Within seconds, we've got all this information. The ball comes off his bat at 88.3 miles per hour at an angle of 24.1 degrees. It knows it's going to go a distance of 314 feet, and it's going to take 4.0 seconds to get there. All right, all that information. This is kinematics. This is what we're learning right now, right?
Look how far Hayward had to go.
Okay, now it's analyzing the players, right? The guy in left field, he was a little slower. It took him 0.05 of a second to start moving to his left when he saw the ball hit. It took the guy in center field 0.02 of a second to start moving. These baseball players are incredible. He hit a bigger top speed than the other guy. He had a better acceleration than the left fielder, and he was a little closer to start with. He was a little closer to start with, and he's the one that ended up making the catch, right?
Completely laid out right off the top of the turf.
So the straight line path from where he was standing when the ball was hit to the point where the ball landed was 80.9 feet. And his path was 83.2 feet. That's incredible. I don't know if you've ever tried to catch a fly ball that was hit to you, but my path would not be that straight. My path would look more like this. I guess that's why I'm teaching physics now, right? But this is incredible. Anyway.
A big league play.
Turner hits one in the air, left center field, long run for Hayward. He dives in! He made the catch in the...
Okay, the ball game is over. So that's pretty amazing. I mean, you start learning these equations and you're thinking, okay, I can figure out how fast a car is going when it goes onto the freeway or something. But boy, some imaginative people took these and took it to a whole new level, didn't they? Pretty good stuff. All right, let's go back to velocity addition now. And if you want to read more about it, it's in the notes here. Okay, so what do we have? Velocity addition. So let's do a boat crossing a river. Here's our boat. Here's the point directly opposite. Here's some point downstream. And we'll be given some dimensions here. This would be A, this would be B, and we've got our water flowing here. Velocity of the water with respect to the ground. Okay, so there's some given information here, right? So we know that. We would also have to know at least the magnitude of the boat with respect to the water, right? The direction, we're trying to find the direction. We'd be given A and B. So there's our given information. And what do we want to do? We want to find theta. Right? At what angle do we need to orient our boat such that we go from A to B? Okay, in other words, we want to go straight across. So think about that for a second. See if you can set that up. Right, so our equation looks something like this. The first subscript has to match, the last subscript has to match, and the two in the middle have to be the same. And this is true even if you have more things moving. I won't give you more than this on the test tomorrow, but if you had like a bug walking across the bed of a truck and the truck was moving, and let's see, maybe the bug was walking across a box in the back of a truck and the box was moving and then the truck was moving, right? You have multiple things moving. You could keep doing these. You have like the velocity, you want to know the velocity of the bug with respect to the ground. And you've got the velocity of the bug with respect to the box that it's sitting on, plus the velocity of the box with respect to the truck, plus the velocity of the truck with respect to the ground. So the first subscript is the same, the last one is the same. These two have to match, and these two have to match, right? So you can keep the bug is walking along a box, the box is sliding in the back of a truck, and the truck is driving down the street, right? So here you've got three things linked together. This equation can be, you can keep expanding it, right? The rule is the same, but as I said, tomorrow you won't get three things. We'll limit ourselves here to two, but I'm just showing you that the equation can keep going here. So once you kind of have that pattern, and I know it's kind of just, we're just kind of memorizing an equation for that, but once you have that, it tells you how you do. This is a vector addition problem. How do you do this? So what's the vector we're trying to find here? This one, the boat with respect to the ground, the boat, when you're standing on the ground watching the boat, it's going straight across the river from A to B. So that vector, I'll draw it in red, that vector is going to look like this, from A to B. The boat is going to have to point one way or the other, right? Because the water is flowing to the right, we know that the boat is going to have to point itself this way, right? Because the water is pushing this way. So we'll add those two vectors. The boat is going to be doing this, and the water is going to be doing, use blue for water, that. So this is the velocity of the water with respect to the ground. This is the velocity of the boat with respect to the water. And there's our triangle. This one's pretty straightforward because it's a right triangle, right? I made it easy. Don't worry, part B is coming. Okay, so what do? We say theta. How would we orient ourselves? We would point ourselves at an angle theta, a little bit upstream, and that is the, what is that? The inverse sine of the water with respect to the ground over the boat with respect to the water. Okay. And then, of course, it's a right triangle, so you could find the speed that the boat is actually heading across the river with, and the time it would take, because you know the width of the river, things like that, right? We okay with this one? Now, let's do part B. We're not trying to get to point B straight across the river. We're trying to get to point C, okay? So find the angle that the boat has to leave. Did I get my sign wrong? Let's see. This is what we have to look and see what's given in the problem here. We're given the speed of the water and the speed of the boat, okay, with respect to the water. So this is given, and this is given. And I'm trying to find theta. So the opposite and the hypotenuse are given, so I'm going to pick sine to find theta, right? If I didn't know the water speed, but I knew this one, then I'd use inverse cosine, right? Or if I didn't know the hypotenuse, but I knew the other two sides, I could use an inverse tangent. You just look and see what's given, and you find the angle from that. Okay. So you're setting this next one up. You're going from A to C now. Yes. But you have all the paper you need on the test, right? Just you can scan it all and turn it in, or not. Those dimensions were given, remember? So let me write our equation one more time. The boat with respect to the ground, that's what we want, right? The boat with respect to the water, that's the speed that was given. If it tells us the boat always moves at whatever 5 meters per second with respect to the water, no matter what angle it's pointed, then that's the velocity of the boat. That's the speed of the boat with respect to the water. We're finding the direction. Plus the velocity of the water with respect to the ground. So which vector here do we know right off the bat? This one, the velocity of the boat with respect to the ground, because we know the boat leaves A and ends up at C, so the velocity of the boat with respect to the ground has to point in that direction right there. And the water was given, right? What am I using? Blue for water? The water was given some amount in this direction, right? And so that means the boat has to point itself in this direction, right? Because the boat to the water plus the water to the ground has to equal this red vector of the boat with respect to the ground. So our triangle looks something like this now, right? Let me redraw it down here. Something like that, something like that, and that one, right? So we know this. This is a known amount. Should we put some numbers in, or it doesn't matter? This is a given amount. We were given the velocity of the boat water, right? We were given this, and this one is also a known amount. We're given this, the magnitude, the length of this line, right? We know that. We know the other one, and we know this angle because that's going to be the inverse tangent of A over B. We were given these dimensions here, A and B. So we can find that angle right there from that. So if you know two sides and an angle, you can find everything else. How do you do that? Law of sines and law of cosines. I think in this one, I think you only need law of sines to solve it. And those are on the formula sheet. Okay, very helpful for velocity addition problems, law of sines and law of cosines. Question about the water vector. The water vector has nothing to do with the spacing. How fast the water is moving has nothing to do with the distance between B and C. So we don't know. I kind of assumed that the water was not moving terribly fast here, and that our picture would look like this. But it's possible that the water, there are three possibilities here, right? One is that the water is moving super fast. You have a big flow of water. We're trying to get from A to C, right? And here's B right here. The water might be moving super fast, so that even though, just like when the boat tried to go straight across the river, it had to angle itself slightly upstream because the water was pushing it down. The boat might still have to angle itself upstream a little bit if the water is moving super fast, right, to get to point C. Oops, what just happened? Right, it could be this situation, or maybe the water is moving at just the right speed that you'd have to point yourself right towards B. Here, A, B, C. The water might be moving at just the right speed that the boat would have to point itself this way to get from A to C, right? Or it's the way I drew it, the water is moving kind of slow. So there's your water, there's your boat, and there's your A to C. In any case, the vector going from A to C is identical in all of these, okay? But it depends on what value is given for that speed of the water. Do we know if velocity of the boat with the water is an angled line or not? So the question is, do we know if the velocity of the boat with respect to the water is an angled line or not? Could it be drawn as a vertical line? So all we're given in this problem is the magnitude of the vector. And the question is, what's the angle? What's the direction it has to point to get you to that destination? Okay, so you can see if you point your vector for part A, where's part A? Come on, oops. For part A, we're trying to go straight across the river to point B, right? Well, you know, if the water is pushing on you a little bit this way, you have to angle yourself that way. You can't point your boat straight at point B, or you're going to end up downstream somewhere, right? So you're trying to find that angle that you're heading, right? For part B, we want to know what angle do you head your boat? Do you point the boat such that you end up at C? It's the same problem, it's just a little more complicated because there's not a right triangle at the end. And then for this, why is theta not at the bottom? Because this is the angle that was given, right? We need to know some angle in this triangle, and theta is actually this one. This angle is theta, right? Because we know B and we know C. We know this distance is A, and we know this distance is B. So theta is this one. But you need to know an angle in the triangle. You use what's given in the problem to figure out one of the angles in the triangle. Once you know one of the angles in the triangle, then you can You can solve for everything. I shouldn't have used a theta here. Is that the problem? Let me not use theta, because I used theta earlier. You're right. We'll call this, what should we call that? Phi? Is that better? Yeah, that's confusing because I asked for a theta. Theta is actually this angle. We're trying to solve for how you point your boat, right? Theta is actually should be like this angle here, right? But once you know the angles of the triangle, you've solved for it. You can figure out theta. I think that's better. Thank you. Is there a formula sheet provided? Yes, there is. Some of you don't have a printer at home, so you can't print it out. What happens is when you look at the exam, it's going to look like it's 5 problems. It's not. It's 3 problems. The last 2 problems are the first page of the formula sheet and the second page of the formula sheet. So they're there. You can view them anytime. Now, I didn't give you numbers, so I can't give you a final answer, but you're using law of sines and law of cosines. Actually, I think you can just use law of sines to solve this, but you have to find this angle right here, right? Once you find that angle, I'll call it gamma. What's happening? Once you find this angle, it doesn't like it. Oh, now it's up here. Okay, so once you find this angle, gamma, using law of sines, then you know phi and you know gamma, so you could figure out theta from that, right? Then you're done. Okay. We went a little over. We got excited, had this fun problem we're working on. Let's take a 10-minute break. If there are any more questions, we can address them then. Otherwise, we'll move on to forces. We'll start our new material. Okay, 10 minutes. I'll pause the recording. See you in 10 minutes. Okay, good. Anything else you'd like to cover before we move on to new material? So the question about Proctorio sometimes doesn't load the exam. Well, you're not using it for the exam, to load the exam, right? So you're writing everything on paper, and then once you've finished, then you're going to get it uploaded into Gradescope. So you're not actually loading the exam into Canvas with Proctorio. It's just, you have a few minutes there after you finish Proctorio to upload your exam. Good. Any other questions? For the practice quiz, Proctorio. So you view, right? You view the quiz in Canvas using Proctorio. You're writing it on paper the whole time, viewing it there, but then you exit out of Canvas and open Gradescope and submit it in Gradescope. Is that what you did for the practice? Okay, if there are any issues, email me your PDF file, okay, as soon as you're finished. But then that'll be the backup plan, okay? Does that work? Okay, email me if you're having any issues. I've had a few people I've been able to work around, come up with something that works for them. You'll have to use your phone to scan the app, yeah, to scan your exam. That's what I'm assuming, yeah. And you'll have about 5 minutes to do that. So that's kind of what I'm aiming for, unless you finish early. Where are we? Okay. I think that's okay. Okay, where are we? Forces. So let's do, let's take a look at this situation. Got a big crate sitting there at rest, and we've got person A over here pushing on it. And person B over here pulling on a rope. Okay, so we want to find, what I want you to do is draw a free body diagram for the box. So what is a free body diagram? It's an image of the box, the block, with every force that's acting on the block. Every force that's acting on the block represented as a vector. So normally what we would do is draw an image of our object. Now, right now, our knowledge is very limited, right? We're a week and a half, 2 weeks into physics 4A. So that means that we don't know how to deal with objects that rotate, right? We will soon, we will before the quarter is over. But right now, we can't deal with rotation and things. We can only deal with objects moving in sort of straight lines, basically, right? Translating, not rotating. So that means that we don't really have to draw the whole dimension of our object. We could just represent it as a point object. Every object to us right now looks like a point object because we can't deal with rotations, but pretty soon we will. So before the end of the quarter, our free body diagrams, we're going to draw the shape of the object and actually where the forces are being applied to the object. But right now, we can represent our object as a dot. And the forces, we can draw the vectors there. Now, by convention, we always draw the tail of the force vector on the object. That way there's we have some kind of rules for drawing these free body diagrams that help us so that they don't get kind of messed up and complicated, too complicated. You won't know which vector's which. So we'll do the tail of the vector on there. So most forces originate from contact, right? So it's a good idea to just go through and think about what's touching the box. So what's touching the box? Person A, right, is touching the box, and they are pushing on it to the right. So I can have a force here, looks something like this. This is the force from A on the block. Okay, if you're getting an error because you need an access code in Proctorio, it means you don't have Proctorio installed in your web browser, most likely. You have to use Chrome, and it's an add-in, or what do they call it, an extension. Add the extension in Chrome, Proctorio, and then you should be able to get in. It should not ask you for an access code. Okay, so that's one thing that's touching the block. What else is touching it? The rope is touching it, right? Not person B. Person B is not touching the block. The rope is touching the block. So we'll add a force, and that's pulling it to the right also. This is a force, the rope on the block. Now, what else is touching it? The ground, right? The ground. And so that's the ground can interact two ways. Usually we split that up into components. I don't know why, but it's usually simpler to think of it that way. It can interact through a normal force, right? Normal or perpendicular to the surface, and it can interact parallel to the surface through friction. So we definitely have a normal force here, right? Force of the ground on the block. And the friction force, what direction do we have friction? Is there friction? How do we know? There is friction, and it's to the left. And we know there's friction because the block is at rest. And person A and the rope are pulling it to the right, and it's at rest. So something must be pushing back in the opposite direction. So we'll add our friction force here. That's the ground on the block. This one here is friction. Oops. This one is our normal force. Okay, so that's everything that's touching our block. What can reach in from a distance and exert a force on something? There's only one force that we're going to learn this quarter that can reach in from a distance and exert a force on something without touching it, and that's gravity. Next quarter, you'll have more, right? Next quarter, there's electric forces and things like that that also manifest themselves at a distance. But for this quarter, we only have one. So think about everything that's touching the object, and then gravity can reach in from a distance. This is the Earth on the block. That's gravity. Okay, so if you look at this, everything is a force, right? Force, 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 force. I used F for all of them. That's not really helping me see what's going on, right? So we like to use special symbols for certain forces. So when we look at this, we know right away it's a normal force or it's tension in a string or something like that, right? So let's change some of these. So T is a good one for tension. Tension in a string or rope. Capital N, normal force. We use a lowercase f typically for friction. Now, the force of gravity, we have a lot of different choices for. Some people like to use F sub g, force of gravity. Some people use W for weight. Either way is fine. It's just that in physics, we have a lot of W's. So in a couple of weeks, W is going to stand for work. And we have another W somewhere else. I forgot what it is. And then W is also a unit we have for watts. That's a unit of power. Anyway, we seem to have a lot of W's. So we can use W for now, and then in a couple of weeks, maybe we'll stop using it or use F sub G, whatever you like. Sometimes you could just write mg. The mass times the acceleration of gravity gives you the force of gravity. Okay, so those cover a few examples that we pop up a lot. Normal force, gravity, friction, tension in a string, but sometimes we just have a force we need to account for, some other kind of force. So we'll just use F as sort of our catch-all generic force. Any other force. Okay. So if we redraw this, we would get a force from person A acting on the block. We would get tension in the rope acting on the block. See, that's a little more, you see the T there and you immediately think rope or string. We have a normal force between the ground and the block. We have a force of friction between the ground. And we actually have two kinds of friction we will learn soon. This is static friction between the ground and the block. And we have the force of gravity, the earth acting on the block. And if you drew your free body diagram correctly, the last subscript here on every one of these should be the same, because this is a free body diagram of the block. Every force acting on the block. So every force represented should be acting on the block. It shouldn't be the block acting on something else, right? So the last subscript should be the same there for everything. And it's a good idea, I think, for, as you draw free body diagrams for the first couple of days, write it out kind of formally with the subscripts there, so after a while, after you do some problems, a few days of this, you can start eliminating some of these subscripts. And so what I would do, my rule of thumb is, if I'm drawing free body diagrams in a problem and there's only one tension in the whole problem, I just use T. I'm not going to put subscripts on there. I can see what it's being applied to, right? If there's only one force of gravity, I just use F sub G or W or something like that, right? But if there are two masses in the system, and so I have two forces of gravity, then I always put a subscript, F sub G1 and F sub G2, because they are different, right? The force of gravity on this object is probably different than the force of gravity on this one. And if they're different, they better be different in your free body diagram. They'd have to have different subscripts. Otherwise, you're going to think they're the same. So, so anytime I only have one of something, I just leave it that way. But if there's more than one, if there are two tensions, or if there are two gravitational forces, or two normal forces, or more, then I put subscripts on them so I know the difference between them. I know which one is which. That's my rule of thumb. Okay, so let's talk about some of these. We've got some interesting forces. The force of gravity does change with mass, yes. So the force of gravity is mg. As the mass of the object increases, the force of gravity between it and the Earth also increases. And you know the difference between the two. So mass is how much stuff something is made of. So the mass of an object sitting on the surface of the Earth is the same as the mass of that object sitting on the surface of the moon, is the same as the mass of that object floating out in space somewhere. Mass is how much stuff something is made of, and it doesn't change. It's always the same. Weight is the force of gravity, the interaction of that object and the Earth. So an object sitting on the Earth will have a certain weight because its force of attraction with the Earth is a certain amount. If that same object is taken to the moon and is sitting on the surface of the moon, it weighs less. It doesn't interact the same with the moon. The moon is much smaller and it doesn't have as big a force acting on it. It weighs less. And if that object was floating out in space somewhere, I guess it wouldn't weigh anything. I don't know, right? It's weight is a force. It's an interaction with a planet or something like that. Whereas mass is universal. It's always the same, never changes. It's how much stuff something is made of. Okay. How do we know the difference? Because of the units, right? The units. So if you're measuring mass, our SI unit for mass is the kilogram. So kilograms, grams, right? That's mass. And if it measures force, it measures in newtons. Now, this is the tricky part here. Force, let's think non-SI units because most of us are used to that. Force is measured in pounds. So you step on your bathroom scale and there's a reading there in pounds. That's a force. It's measuring the force that your body is exerting on that scale, right? And opposite that, on the same dial, it says kilograms. That is wrong. It's not measuring kilograms. It is assuming that you're using that scale on the surface of the Earth, which is probably a good assumption. But if you take that scale and to the moon and stand on it, it will read a completely wrong value because it's labeled kilograms. It should be labeled in newtons because that's your force. That's the force acting on you. So for forces, newtons or capital N. And for mass, kilograms. Do you know what the unit is for mass? Non-SI unit, right? We have pounds for force. What do we use for mass? Slugs. The slug is the unit for mass. Okay. So in our SI units, force is in newtons, and that corresponds to slug is mass. Slug is mass. This would be like non-SI. This would be pounds, right? should be a D over there. And this would be the slug. So we're used to pounds, right? We use pounds all the time when we weigh ourselves. This weighs this many pounds, that weighs that many pounds. We're used to that for weight, and we should start to get used to thinking newtons for weight and kilograms for mass. Okay. All right. So let's talk about a couple of these forces. How do they manifest themselves? Normal force. It's a good idea. Point about a balance. So if you're using a scale, sometimes you've seen the word scale, sometimes you've seen the word balance, right? A scale usually uses like a spring or something like that to measure something. It's measuring force. So it should measure in pounds or newtons, it would be the correct units. My dog is getting excited. Pounds or newtons. So when you step on your bathroom scale, it reads pounds, and it should read newtons, not kilograms, because that's what it's actually measuring. It's measuring force. But if you've seen maybe in lab, well, you haven't, maybe hopefully one day you will get into a lab room and touch some equipment, and you will see we have a balance in there. And you put something on there and it swings, you move some weights and it swings back and forth until it's level. And then you record how much weight is on one side, and that is equal to the mass. It's how much mass is on one side, and that equals the mass on the other side. And that actually measures mass. You could take that same balance to the moon and you would measure the same mass for the object. You could use it anywhere, because it's putting mass on one side, mass on the other side, and looking to see when they balance out and it becomes level. So I think that popped up here, a balance popped up here. Okay, so a balance measures mass, a scale, weight. Normal force. So normal force is a little tricky. We've got the situation where I need to, let's do this. There we go. Okay, there's my mug sitting on the table. And so there's a normal force. The table is pushing back up on our mug. How do we know? Because the mug's not falling down, right? The only force acting on this mug, there are only two forces, right? Gravity pulling down on it. Gravity pulling down, and the table pushing back up. And so the table is pushing up with the weight of the mug, right? The weight of that object. But wait a second. Now I just put my phone on top of it. Now what just happened to the normal force? It got bigger, right? Now the force of gravity is still the same, pulling on my mug, but I added another weight on top. So there's more than just the mug pushing down on the table. The table is pushing back with the bigger force now, right? Now I'm going to add another object to it. I'll put my mouse on there. Okay. Now the normal force just got bigger again, right? So the normal force can change. It can react. So let's think about that. So why is that? Well, if we zoom in, we need a model, right? We need something to help us picture what's going on. Once we have a picture of what might be happening, then it's easy to understand this phenomenon. So our picture is that the surface of that table is made up of a bunch of molecules bonded together, right? So if we zoom in with our microscope on the surface, we've got an atom over here, or a molecule, and we've got some kind of a bond to another one over here, and we've got some kind of a bond to another one. And here, and we've got some kind of a bond to another one. And we had something sitting here, right? So our surface normally would be nice and flat, but we take a box, right, and we sit it on our surface, and microscopically, the surface gets deflected a tiny bit. And those bonds, those chemical bonds between the atoms are like springs. And when they stretch a little bit, like a spring, when it's stretched, it pulls back with a certain force, right? But a spring, you know, as you stretch it more and more and more, the force gets bigger and bigger and bigger. It's harder to stretch it. The first centimeter, it's easy to pull the spring out, right? The second centimeter, it's harder. The third centimeter, it's even harder, right? As you stretch it, the force gets bigger and bigger. And so that's what's happening here. It's like those chemical bonds are like springs between the atoms. And as you put something on the surface deflects a little bit. And so what happens? You get a force in this direction, right? From the surface interacting with it. And as you deflect that surface more and more, even on that microscopic level, that force gets bigger and bigger until what happens? Until the force is so, the deflection is so much that those chemical bonds break and you've broken your table, right? And you fall through. So that's our model for normal force. So you can kind of see now how it reacts to things, right? You can't just say, oh, a normal force is always this amount, right? You have to look at the situation and see how much, what is that normal force? It reacts. As I take my my mug and I put it on the surface and I get a certain normal force equals the weight of the mug. Then I put my phone on top of that and I get a bigger force, right? And I put something else on top of that, or I lean on it a little bit, and the normal force keeps getting bigger and bigger. The other force that we're going to deal with is friction. Let's talk about friction for a minute. So friction is another one that could, friction is a complicated force because we have two kinds, right? We have static friction and kinetic friction. We'll learn more about that next week. But the idea is that when the two surfaces are stationary, there's no motion between them, that's when we have static friction. And when there's sliding between the two surfaces, when there's motion between the two surfaces, that's when we have kinetic friction. And so let's think about friction for a second. So what would I do without that coffee mug? We've got our coffee mug here, and it's sitting at on the table. Nothing is pushing on it, right? Nothing's there pushing on it. So is there a friction force acting on our coffee mug now? No, no friction force, okay? Now I'm gonna take my well-calibrated finger and I'm gonna push with the force of 1 Newton. What's the friction force acting on my mug now? It's 1 Newton in the opposite direction, right? Because my mug is not moving. So you have to think a little bit about, we haven't talked about acceleration yet, But if there's a net force acting on our object, it's going to go in that direction, right? It's going to be accelerated in that direction. So if I hold my object up like this and I let go of it, there's a net force pushing down. I'm not going to do that because there's here. If I hold my object up like this and I let go of it, the force of gravity is acting on. There's a net force in the downward direction. It's going to go in the downward direction, right? And if I push on it and create a net force in that direction, it will go in that direction. So if the object is not moving, we know there cannot be a net force acting on it. So if I'm pushing this way with 1 Newton and the mug isn't moving that way, something else must be pushing in the other way, in the other direction with 1 Newton. And that would be friction from the table. So if I push with my well-calibrated finger 1 Newton this way and the mug doesn't move, then I must have a 1 Newton force in the other direction. And if I increase my pushing force to 2 Newtons and the mug doesn't move, we know friction is pushing back with 2 Newtons. And now I'm pushing with 3 Newtons and the mug's not moving, so there's a friction force of 3 Newtons. But if I keep pushing harder and harder and harder, eventually it breaks free and it moves in that direction. So our friction force is kind of complicated. So let's think about what could be causing that. Well, let's zoom in again on our surface. We won't go quite down to the atom level, but we'll go close. Okay, so we're going to zoom in on our surface. And the surface is going to have some roughness to it if we zoom in close enough, right? It's not going to be perfectly smooth. There's some roughness to the surface. So our surface might actually look like this, okay? Yeah, there's still friction when the object moves. The question was, when the object started moving, and when I pushed hard enough and got the mug to move, was there still friction? Yes. We call that kinetic friction because there's sliding or slipping. There's motion between the two surfaces. We'll get to that. Don't worry. Now let's zoom in on the bottom of the mug, right? There, our object, whatever it is, and we've got an object that looks something like this, maybe. Right? And we're pushing on it. So what happens right here? We have two surfaces that are sort of pressed up against each other, like a normal force, right? Like you pushing on the table or pushing on the wall. Those two surfaces are pushing on each other, and so it's preventing the object from sliding. And you push harder, and what happens with the normal force? What happens when you push harder on the table? The table pushes harder back on you, right? What happens when you push even harder? It pushes even harder back. So that's what happens here. You get a couple of spots like that, where you have these surfaces pressed up against each other. And if you push one harder, the other one pushes back harder and it doesn't move. And so static friction can get bigger and bigger and bigger until you push so hard, it slips and slides across the top. And then there's just a smaller interaction between the surfaces. You still have two rough surfaces trying to slide across each other. So there's still some friction there, but it's different than static friction, right? Static friction is caused by this surface to surface normal force pressing, and then you dislodge it and it slides and you still have two rough surfaces interacting, right? But it's a smaller force. So when there's motion between the two surfaces, we call that kinetic friction. That's because kinetic means motion. And when there's no motion, when the two objects are stuck, when there's no motion, we call that static, right? Static means no motion. Okay, so that's, if you kind of have this in your mind, this model in your mind of how that might work, then I think that's helpful, because a lot is built on this. A lot is built on the fact that that normal force can increase and decrease and change, and you kind of have to understand how that happens. And a lot is built on the fact that static friction can change. It can increase, it can decrease. You have to look at other things in the problem. Now, once that object starts moving, once it goes into kinetic friction, we can calculate that. That never changes. Kinetic friction is kinetic friction. It doesn't matter if the object is moving at 1 meter per second or 10 meters per second or 100 meters per second. We deal with kinetic friction the exact same way. It just depends on what the surfaces are. Some surfaces, of course, are smoother and slippery, and some are rougher and harder. And so that changes how they interact with things. But we know how to deal with that. We get a coefficient that is dependent on the surface, and that helps us figure out the friction force. Okay, so we've had this nice introduction to forces and free body diagrams. And what you'll probably do is, as you start practicing your free body diagrams, as I said, think about the labeling, the subscripts, things like that. And it's probably a good idea for the first, day or two, whatever, put all the subscripts, be formal, think about what's causing what. Is this force acting on my object? Every force acting on that object is included in the free body diagram for that object. Okay? And then after a couple of days, we'll, start dropping the subscripts. Just use them when you need them. If you have a situation that has two masses, they better be labeled differently. The two forces better be labeled differently. If there's two different tensions, they better be labeled differently, all right? Or you're gonna get confused. Okay, I think that's a good stopping point for today. We will continue with free body diagrams Monday. Tomorrow, no Zoom meeting, right? You just log into the Canvas site. You set it up there. It becomes available at the normal start time for the class on Friday, which is, what time is that, 11 o'clock? And then it gives you an hour, and then upload to Gradescope. Gradescope will go another 5 minutes beyond that hour or something like that. And practice today. If you have any issues, email me. I've been able to help people out, come up with some workaround, figure things out. So that's my recommendation. Don't get surprised on the day of the test. Okay, I'm going to stop the recording now, and I'll stick around, answer questions. We also have an office hour, and I told my other class that I'll give priority to your class from 4 to 4:30. So if you can make it then, that would be great. Okay. All right, so I will stop the recording.